Okay, we're all being recorded here, so be careful what you say. All right, I first want to say, let's see, people, when I assign a special problem, it's generally due the next class, unless I say it's not. Okay, so the special problems are really due today, but if you quickly do them after class and email them to me, I will accept it. Somebody pointed out to me that on the practice problems, I made an error in number 84 and number 72. A couple of errors. I already gave out gotcha slips for these errors. I don't think they're that serious in the sense that it wasn't like a really bad mistake, just like incorrect by maybe a 0 or something. So it was kind of the right way to do the problem, but so anyway, I'm going to correct these and I'll put it up on Blackboard, but it's, if it confused you, if you thought that I made mistakes somewhere when you were practicing for the quiz today, I did make a couple of mistakes. I also want to say that I always arrive early to this room, to the classroom. And I'm usually here like a little after 9, like 9:05 or 9:15 or something like that. And if you want to bring your questions, that's a good, that might be a good time to do it. I'm in my office right after class. I'm there for hours. So even if you have a lab and you still want to see me, you could let me know and I'll stay there till after your lab and meet you. I met quite a few students yesterday afternoon in my office. I don't have office hours then, but people contacted me and I was there. So I may have to revise the office hours, because if I'm going to be there, I should just say that I'm going to be there. But anyway, I just want to let you know that I do arrive early. I actually am in my office probably at 8:15. But I'm mostly like going over my notes, so I don't really necessarily want company then, unless you have a burning question. So no, that's not something to look through. That's something to hand in if you have a special problem done. Yeah. Okay. All right. So I want to just start with where we left off. Where we left off last time was something called Z, which we called the atomic number. If you've had chemistry before, this is all pretty basic to you. The atomic number is the number of protons in the nucleus. And here's another thing. If the atom is neutral, now remember, protons and electrons have equal and opposite charges. So if you have a neutral atom, it means that the number of protons and the number of electrons has to be the same, okay? So if the atom is neutral, then the number of electrons is also equal to that number of protons, which is equal to the atomic number. I just want to let you know that what I often do is I write E for the number of electrons and P for the number of protons and N for the number of neutrons. It just makes it a little easier. Okay, so the atomic number is the number on the periodic table. On the one that I gave out, it's in the upper left corner. Some periodic tables, it's right in the center, but that's the atomic number. That's the number of protons. That tells you that you know what atom you're talking about. That tells you how many, what element it corresponds to. Okay, but we can also, there can be ions. So ions form by an atom gaining or losing one or more electrons. Okay, so you can have negative ions and positive ions. Okay, so because of that, the number of electrons doesn't necessarily tell us what atom, what element we're talking about. You have to look at the number of protons in the nucleus. So you always use the number of protons in the nucleus to identify the element that you're talking about. Okay, so that's the atomic number. We also have something, in most books, it's called A, which honestly, I hardly ever use that symbol, but I do use the mass number. The mass number, okay, remember now that what gives the atom mass are the protons and the neutrons. And a proton has this just about the same mass as a neutron. So the mass of one proton is equal to the mass of one neutron, and this we call one atomic mass unit, AMU. Later, we'll be able to relate to grams and things like that, but that's not for yet. So P plus N, that's the number of protons plus the number of neutrons, is the mass number, okay? The electrons do not contribute to the mass because electrons basically have, we call negligible mass. We really mean compared to the mass of the atom. They're not negligible to some other things, but they certainly are negligible for the mass of the atom. So the mass number is the sum of the protons plus the neutrons. And the reason why we call that the mass number is because that is the mass of the atom in atomic mass units, okay? Because those are the only contributors. Well, I see I'm going to have a little trouble with inserting a space today, but here we go. So and this is the mass of an atom in atomic mass units, okay? Because that each of those things contributes one. Okay, so let me just do a helium example. So helium has 2 protons, so Z equals 2. It has 2 protons, okay? It also has 2 neutrons. These are, of course, in the nucleus. Okay, so the mass number is 2 plus 2. That's the number of protons plus the number of neutrons, which is 4. So that means that one helium weighs 4 atomic mass units. Okay, and so that's the mass number. And the way we write this is we write HE. We put the mass number here, which is 4. So this is where we put A, the mass number. Down here, we put Z, the atomic number. Okay, so we could write that helium 4-2. So let's consider another example. Supposing we consider carbon 12-6. All right, so what does that mean? All right, that means that 12 is the sum of the protons and the neutrons, because 12 is a mass number. Okay, so what we can do is figure out, because we're also given here, this is Z, so this is the number of protons. All right, we can take 12, the mass number, and subtract the number of protons, 12 minus 6, and we get the number of neutrons. Everybody with me? If you have a question, it's a good time to blurt it right out. All right, so that's 6. So we have 6 neutrons. We already know that we have 6 protons because we were given the atomic number here as 6. So what is the number of electrons now? So you can look at this carbon 12-6. You see there is no charge written down. It doesn't say plus, it doesn't say minus. So it's a neutral atom. So 12-6C is neutral. If it were charged, it would say +2 or minus whatever. It doesn't, so it's neutral. So the number of electrons is the same as the number of protons. So because 12-6 is neutral, it implies that the electrons equal the protons, which is 6. So that means there's 6 electrons. Okay, so you should be able to look at any atom that's written with its mass number and its atomic number, and you should be able to figure out the number of neutrons. So for boron 11.5, what does it weigh? What is its weight? What is its mass in AMU? Yes, 11. My pen is going to do this to me. It's because I'm recording, I'm sure. Mass is 11 AMU. So 11 is the sum of the protons and neutrons. The atomic number is 5. That's the number of protons. So 11 minus, well, so 11 is 5 plus the number of neutrons. So now I subtract 5 from both sides. And so the number of neutrons is 6. So I already had 5 protons. Again, this is neutral. So the number of electrons is also 5. Okay. So let's go ahead and look at activity 1, where there's a little more practice with this. This is chapter 2. Okay, it looks like this. So let's do magnesium 2612 and silicon 2814. So take a few minutes, just really not very long, to try to work out what is the number of protons, what is the number of neutrons, and what is the number of electrons. Remember that this is the sum of the protons and neutrons. And if you finish that, just go on to the next two, but I should explain something about those actually. Okay, so what is the thing that you know immediately, but from when you look at this, what is the thing you could get the easiest? Yes, and the number of protons is just this number right here, right? Okay, so what is the number of neutrons? How do you figure it out? Right, it's 26 is the sum of protons and neutrons. 26 minus the number of protons is the number of neutrons. So 14 is the number of neutrons. And the electrons here? 12, because there's no charge. So it means it's neutral. Let me get rid of this line. It's actually confusing. No charge. So the number of electrons equals the number of protons. All right, so that's pretty straightforward, I think. Here, what's the number of protons? 14. P plus N is 28. P is 28 minus N. Oh, sorry. N is 28 minus P. So it's 28 minus 14, which is also 14. So a lot of times the neutrons and protons turn out to be the same. And the electrons here, it's the same as the protons because it's neutral. So you have equal numbers of protons and electrons, 14. Okay. Oh, wait. Oh, yeah. All right. So now we move on to slightly harder. Here we have one negative charge. So that means that this atom has acquired an extra electron. One extra electron, meaning that you have one more electron than protons, right? So we know the number of protons is 9. So what's the number of electrons going to be? 10, absolutely. And of course, the sum of protons and neutrons is 19. So the neutrons is 19 minus P, or 19 minus 9, or 10. So that's how you figure out the number of protons, neutrons, and electrons for an ion. Here we have a different charged ion. Here we have a positive charged ion. So what does that mean happened to the cobalt atom? Yes. No. The number of protons doesn't change. It's the number of electrons. Yes. That's right. So it's only the number of electrons that changed. I thank you for saying that, because I got to point out, that wasn't the way to do it. So it's a positively charged ion. So it means this atom lost 2 electrons. So now there are 2 more protons than electrons. So now an ion now has 2 more electrons than protons. Okay. No, oh, wait. 2 fewer, sorry. Yeah. So it will have 27 minus 2, or right, 25 electrons. Sorry, I said that. E is 25. P is 27. We know because the atomic number. 59 minus 27 is 32. So here we have an atom that has quite a few more neutrons than protons. But anyway, that's how you do those examples. So what I want you to do next is look at the periodic table and look for boron. It's got a Z of 5. This is what it looks like on your periodic table. Okay. So on the periodic table, the Z is written here, or a lot of times a different periodic table might have the 5 here. It's basically the number that increases incrementally as you go across the periodic table. And if you look at it, this number here indicates the mass of 1 boron atom. Now, if I go back a little bit, when I did boron, here I had boron 11.5, right? And we had a mass number of 11. So that means that this guy has a mass of 11 atomic mass units. So if that's the case, why is it that on the periodic table it doesn't say 11? Yes. That's right. There's something called isotopes. And isotopes are atoms with the same number of protons. So they identify with the same element, but different numbers of neutrons. Okay. Same number of protons, but different numbers of neutrons. Does this affect the chemical properties? No. Does not affect chemical properties. Anybody know what kind of properties are affected? Say again? Nope, not physical. No, that would be chemical. Let me just tell you, okay? It affects like things like nuclear decay. So it affects nuclear properties. Like radioactive decay. Which is, I guess, a special kind of chemical property, but it's not the ones we study in chemistry class, okay? So the question is, where does that 10.81 come from? And really, Juliana, right? She pretty much gave the answer. Where does AMU come from? And what it is that there are 2 stable isotopes of boron. And those stable isotopes are boron that has a mass number of 11 and boron that has a mass number of 10. Notice they both have 5s, both have the same atomic number, okay? And that 10.81 is the average mass. So I ask you, if it's an average, why isn't it 10.5? Nope, electron mass doesn't matter. Nope, yep. More naturally occurring. So he says it's the one that has, it's because the one with, well, I'll paraphrase it, the one with the mass of 11 is more naturally occurring. And that's absolutely right. There is a greater percentage of boron atoms in the world with a mass number of 11. Okay, so in fact, what the amounts are for boron 11, this has what we call a percent natural abundance is 80.10. Trying to keep track of the time. It's plenty of time. And boron 10 has a percent natural abundance of 19.90, whatever's left. Okay, so you could see that. So what we call this average, it's really what we call a weighted average. It's weighted by the amount of that particular isotope of boron. So because there is more boron 11 than boron 10, it counts more in the average, because this is how we figure out the average. So the average mass that you see on the periodic table is the percent, well, okay, let's just call it, okay, so you could express the natural abundance as a percent, or you could express it as a decimal. If you express it as a decimal, then we call it just the natural abundance. So you take the natural, I'll give you an example, abundance of isotope 1, and you multiply that by the mass of isotope 1, and you add to that the natural abundance of isotope 2 times the mass of isotope 2, right? If it was 50-50, you would end up with something that's halfway between the two. But here we don't have 50-50. If you have more than one, you would just keep doing this. If more than 2. And you just keep going. So let me show you how that works for boron. First of all, I need to use the mass of these different isotopes. And these masses are not exactly integers. They're not exactly whole numbers, but they're very close. And the reason that they're not exactly whole numbers is something you'd have to learn in particle physics class, not in chemistry class. So I'm not even going to go into that. But the mass of 11 boron, notice I'm not bothering to put the 5, because boron is always 5. So I don't have to put that in there. A lot of times the atomic number is left off and we just say boron 11. So we call this boron 11. Okay, so mass of boron 11 is 11.009305 atomic mass units. So notice it's almost exactly 11, but not quite. The mass of boron 10 is 10.012937 AMU. Okay, so it's almost a whole number, but not quite. And so now the average mass of the boron, waiting for my pen to come back, average mass of boron that you see on the periodic table is going to be 0.8010. So where did that come from? Notice that was 80.10%. This is what I call the natural abundance, 0.199. In other words, when you take the percent, you divide by the 100. Okay, so those are the numbers that are used in here. That would be multiplied by 11.009305, which is up here. And you would add to that 0.1990, which was the 19.90%, times 10.012937. Okay, and when you do that, I'm actually going to tell you what the answer is. You get 10.811024, which we would round to, well, I'm just going to tell you that it comes out to 10.811. We'll deal with the rounding when we do an example together. And what you see on the periodic table is 10.81. Periodic table that I gave you only gives you 2 decimal places, but that's what it comes from. It's a weighted average of the stable isotopes, taking into account the natural abundance of each one multiplied by the mass of each one. Okay, so if you look at the periodic table, you will see that many masses are not near whole numbers. Take a look on the periodic table. Many masses are not near whole numbers. And now you know why. It's because what it's giving you on the periodic table is an average mass. And it's a weighted average mass of all the stable isotopes. Okay? So if we look at chlorine, for example, on the periodic table, 17 Cl, I don't know, 35 point, what does it say, 453? Okay, that's one of the ones I memorized. So this is nowhere near a whole number. It's not 35, it's not 36, it's not 30. And what it is for chlorine, you have chlorine 35, which is 75% natural abundance. And you have chlorine 37, which is 25%. And you can see that the number there, 35.4, this is closer to this to 35 than 37. Why is that? Somebody tell me why that is, that it's closer to 35? Yes.
If you were to round the number even up, you can't round it up, that's rounded down. You're rounding it.
Right, but why is the number around 35.5 and not around, why is it close to 30? Close, yes. More what? Abundant? Yes, it's because Cl35 is 75% abundance, so it pushes the average closer to that value. Okay. Yeah. All right. So that's why. It's because there is greater natural abundance for Cl35. That's why. If you look at the periodic table, you will see that some elements, many elements actually, do have masses that are near whole numbers. Oh, well. And a very nice example of that is carbon. Carbon 6, 12.01. That's what it says on the periodic table. And that is because carbon is mostly carbon 12. I mean, the vast majority is carbon-12. There's only tiny amounts of carbon-13 and carbon-14, which are still detectable and are actually very important. What's carbon-14 used for? Anybody know? Yes. Yeah, that's dating, figuring out how old something is by carbon dating. That's very important. Carbon-13 is very important in figuring out structure of molecules using nuclear magnetic resonance spectroscopy, which is a technique that's used all over science, just absolutely all over. So even though they're very tiny amounts and they don't really change the mass is so close to 12, but they're still very important. All right, so let's just go to this activity 1 and 2. Number 2. What is the average mass of these atoms or molecules? So A is aluminum. Okay, so yes? Say that again. I do post these notes after class. So I don't really think I need to, anyway. All right. So aluminum. So I'm asking, what is the average mass in AMU of these atoms or molecules? And first I give A and B are both atoms. B is barium, A is aluminum. So all you need to do to answer this question is look on your periodic table. Look for the mass that's written underneath the symbol. And what is that for aluminum? So 26.98 AMU is the average mass of one aluminum atom. That's all you have to do. For barium, you look on the periodic table. What does it say for barium? Second column, a few down. 137.3 AMU is the average mass of one barium atom. Okay, so now we start to think, okay, how can we apply this to molecules, right? Molecules have more than one atom. That shouldn't be a problem. So let's do C, which is SO2. Okay, now what you do is you look on the periodic table for your sulfur and your oxygen. Sulfur, oxygen. These are 16 and 8. And the masses are given here. But you could get them off your periodic table. And you take a look at the formula. And you see in this formula, you have one sulfur atom. Okay. What does one sulfur atom weigh? 32.06. I multiply by 1, I get 32.06 AMU. Okay. But I have 2 oxygen atoms. So I have to multiply the 16 here by 2 to get 32.0. Oops. Yes, that's right. And then I add this up, and 64.06 AMU is the mass of one SO2 molecule. And it is the average mass of an SO2 molecule based on the masses of the average mass of O and S. It asks you to round this to the ones place, so it would be 64 AMU to the ones place. Okay, so that's SO2. The next one is PF6. Why don't you do PF6? And then you could also work on C2H4O2 using the same technique. Look up each of these on the periodic table and multiply by the number of atoms present in the molecule, just like we did for SO2. And there's another example that's done on that worksheet in case you need to see it in writing. It's done for carbon dioxide. So if you look up P in the periodic table, you get 30.97. Fluorine on the periodic table I gave out, I believe it says 19.00. Are these numbers right? Did I do them right? I do make mistakes. You can get a gotcha, you know. And so this adds up to 144.97 AMU, which is the average mass of one PF6 molecule. It asks you to round this to the ones place, even though honestly the sig figs, you should probably keep the 2 decimal places, but it asks you to round to the, this is rounded to the ones place. Okay, and then over here we have a slightly more complicated one. 2 carbons, so 2 times 12.01, 24.02. 4 hydrogens, that's 1.008. And we have 2 oxygens, which is 16 times 2. And you add all these up. So if you were just expressing this to the correct sig figs, you'd have 60.05 AMU. Since you're asked to round to units place, you would round it. So rounded to the units place, it's 60 AMU. So this is something you need to know how to do, because we will be doing the very same thing using grams instead of AMU in just a week or so. Okay. So, okay, it might be nice to know, well, how are masses determined? So remember, I told you that the boron 10 has a mass of 10.012937 AMU. And the mass of the boron 11 is 11.009305. So I guess what I'd like to do is ask the question, how do they get those numbers? How is it determined? How are these precise masses determined? So I'd like to talk a little bit about that. And this reflects, or this is really about what you're going to be doing in lab next week. Okay, so I want to answer the question, how do they get, those scientists, how do they get the precise masses of different isotopes of atoms? And also, how do they get the percent natural abundance of each of those isotopes? And this is done using a technique called mass spectroscopy. And in the lab next week, you're going to learn about a technique called gas chromatograph-mass spectroscopy. And I'm very sorry that our building is being torn down from the inside out. So we actually have a GC. We affectionately call this the GC Mass Spec. And we have one in the department, although I think we paid some movers a lot of money to carefully move it to a storage facility for the next 2 years or 1 year or however long it takes. And so we don't have that to show you anymore. But it's a wonderful instrument, and it's the mass spec part of it really that answers these questions here. But this particular instrument that we have, I thought I would tell you about it because because it is, like I said, the topic of lab next week. So this is a very sophisticated instrument. I believe it costs over $100,000. So it's a kind of a Cadillac there. And it can do this, and it can do many other things as well. All right. So you can get very precise masses of isotopes. You can get percent natural abundances, but also it can analyze mixtures. And these can be mixtures from crime scenes. It can contain blood, other liquids. It contain mixtures of drugs. Athletes could be tested. Athletes' urine samples or blood samples. And what this instrument can do is, if it gets a mixture, it will first separate the mixture into its components, which could be compounds or elements or whatever. It separates the mixture first, and then it analyzes the mass of each component. Okay. And it in doing so, it can determine structure. So you can end up with the formula and also the structure, because as you might know, there can be different formulas. There could be the same formula for many different structures, and the mass spec will even tell you which of those structures is correct. So this part is the gas chromatograph part, and this is the mass spec part. And this figure here, let me move it up a little. This figure here is the mass spec part, okay? So what happens is, wait, let's see. I have to skip something here. Oh, I forgot to tell you about the GC part. Okay, so in this part, it separates the mixture into components. How does it do that? What it does is that the sample, whatever you put in, the sample is vaporized. So it's heated until it all turns to a gas, okay? Then what happens is another gas, which we call a carrier gas, which is helium, flows with that sample through a column. Okay, so this flows through something we call a column, which I know you picture a column as just being a long, like in front of a building or something, but that's not quite what it is here. Here, it's basically a long path. You have a long tube, and actually it's a very windy tube, and it has a coating. You don't have to know this. This is like just to know for lab, like to make you more comfortable with what the heck they did. There's this column, and it's like 30 feet long, and it has a coating that molecules might or might not stick to. And the different molecules in the sample, the different components in the mixture, will stick to the column with a different amount of stickiness. And so what it does is it ends up separating them. Do you remember maybe in high school you did paper chromatography? Maybe not because of COVID, but that's where you put something in that's a colored sample, you let a liquid flow through, and it separates into different colors because the colors stick to the paper in a different amount and stick to the solvent a different amount. Anyway, so it flows through this long column, and because of the stickiness to the column that differs, the stickiness to the column differs, and so they separate. This separates the components. This column is 30 feet long, but it's windy. It's not, so it's in this compact instrument. Okay, so then what comes out of the GC, so this is really, what comes, the GC part is right here, has that column and everything. What comes out is separated components, then generally compounds, you could have some elements, it would be atoms, okay? And so each of these components then arrives in the mass spec part. So this is the mass spec part of the instrument. And I gave you a picture of this, so you don't have to try to copy it because it's really ridiculous to try to copy it. Okay, so this is what happens. And I'm going to illustrate this with an example of the very, very simplest type of thing that you could put in a mass spec. And that is a single, an element. So what would happen if we put the element magnesium into the mass spec? So we put, let's say we take a sample of magnesium. Okay, so it goes in here. And what this is showing here, it says a heater vaporizes. Well, what I really wanted to point out is that there's an electron beam source. So the Mg goes in here, and now these magnesium atoms here are bombarded with electrons. And what happens when these electrons hit the magnesium, you might think that you might end up with a magnesium with an extra electron, but that's not what happens. Those electrons are coming in so fast, they knock other electrons off of magnesium. So you had magnesium with a bunch of electrons, and now you have one fewer. You end up with a magnesium ion and 2 electrons. So you see what happens? An electron hits Mg, and it knocks another electron off. So now you have 2 electrons instead of the 1 electron, right? And you have an ion, a positive ion, a magnesium that's lacking in one of its electrons. And so this is what happens over here in that part of the chamber. Okay, so now you have these Mg plus ions. Okay, and they get accelerated in here. What happens here is that the plate becomes more negative. The plate here has a negative charge, and negative attracts positive. So the positive ions are going to go through here, and all those leftover electrons are going to go somewhere else. That what comes around the bend here are these positive ions. Okay, now, in a lot of instruments, the next step is a magnet. The one that we have isn't quite like that, but I don't care. It's easiest to explain what happens with the magnet. Now, a magnet bends particles that are charged. The heavier ones don't bend as much. They don't get affected by the magnet as easily, but the lighter ones bend more. Now, I said we have a sample of magnesium, but magnesium actually has 3 isotopes. Magnesium 24, magnesium 25, and magnesium 26. So while I said you have magnesium in here, you have to realize that you have some magnesium that's 24, some that's 25, and some that's 26. And all of them are coming around the bend here. Which is going to get bent the most? 24, because it's the lightest. So the Mg24 is going to go down here. And so you will end up with like a dot over here representing the Mg24. The 26 is going to get bent the least. So it'll end up over here. This is a detector that can detect these positive ions. So the Mg26 will be over here. And the Mg25 is going to be partway in between. Halfway, I guess I should say. And that would be the Mg25. Now, when you look, so the detector would look like this. It would have these spots, and they'd be different intensity. I'm going to tell you why I drew it this way. I drew with a really big dark spot at 24 and lighter spots at 25 and 26. Because why do you think I would do that? There's more of, right, so what would you say about the natural abundance of Mg24? Yes, this tells you that this Mg24 has the greatest natural abundance of all the isotopes. Okay, but it's not that, you look at a thing with a a dark dot and two lighter dots. You know, that's not really going to tell you enough precise information. So what's done is this is translated into a diagram, which we call a mass spectrum. And it's a plot of mass on the x-axis. So this is mass and intensity on the y-axis. And so at a 24, you're going to have a big peak because you have the greatest intensity. You have most particles there. At 25, you're going to have a little peak. And 26, you also have a little peak. Okay. And it's from the intensities of these peaks that you could figure out the natural abundance. Okay. The intensity is proportional to the natural abundance at that mass. Okay. So what I'd like to do next is just start to do activity 2. Let's turn to activity 2. And what you see there, this is a mass spectrum from magnesium going into the mass spectrometer. And you see that there are 3 lines. You could see that the third line is slightly taller than the second line. Okay, but the first one is really dominant. And so what the instrument gives you as its output is it gives you the intensity as a number. So notice you have a much larger number for a magnesium 24, and you have smaller numbers for the other ones. In fact, these are almost the same, but you could see 11 is a little bit higher than 10. Okay. The instrument also gives you not just to the nearest ones place here, 24, it gives you many, many places. Okay, so that can be gotten from the mass spectrum as well. So these are the precise masses of these 3 isotopes, and these are the intensities. Okay, so how can we figure out the mass of magnesium that you see on the periodic table? What is the mass of magnesium on the periodic table? Take a look. You can see it's 24.31. Okay, 24.31 is the average mass from the periodic table. So what you need to do is first find the natural abundance of each isotope. So how are you going to do that? What you want to do is you want to add up all the intensity, the total intensity, which is like the total number of particles hitting the detector, and find what fraction or what percent is due to this one. So how would I do that? I would take and get the total intensity first. That's the sum of all 3. And then to find out how much of that is due to magnesium 24, I would take this number over the total. Okay, so it's telling you, figure out what percent of the total intensity is due to each individual isotope. That means taking the intensity of each peak, dividing by the total, and converting it to a percent. So let's add up all those numbers first. Anybody? Now give me all the digits. How many 5s? 555,555. 505. Oh, 505? Yeah, all 5s. Okay, so now if I want to know that this is from 24, this is from 25, and this is from 26. If I want to know the percent natural abundance of 24 mg, I will take the amount that was due to 24 mg and divide it by that and convert it to a percent by multiplying by 100. So I'd like you to do that and do that for the other ones as well. Yeah, and I'll start to think about giving out that quiz. So you do that, and then please just sit with at least a seat between you before I give out the quiz. And just try to sit in every other row here. So like the first one, the third one, the fifth one. Right here. So we're going to each. Yeah, that's the amount of the intensity, and that is the percent actual one. So take a couple of minutes to finish this problem, and then you can do your moving around. You're going to be doing something very much like this in lab. That's why I'm going over this with you. And keep all your sig figs. There's 6 significant figures here on the top one. Yes, when you multiply by, or if you don't multiply by 100, it's just a decimal. But yeah, if you do, then. So notice you have 5 sig figs here, but you have 6 here. Okay, so that's the answer. I'm actually going to stop recording. I don't know what section it is. Sorry.